Okay, so in the last video we had just talked about saturated and unsaturated solutions and how to interpret them with a solubility curve. These are solubility curves for solids, and generally you will notice that as you increase the temperature, the solubility of how much solute can dissolve in 100 grams of water, which would be the solvent, increases generally, right? Well, that's not the case of what happens with gases. So for solubility of gases, the opposite is true, okay? So it is opposite for solids. What happens as you increase temperature, dissolved gas will decrease, okay? And this makes sense to me. I want to tell you a little bit story about me, though, and what I was thinking about when I was in high school. I had always heard that fish need oxygen in order to breathe, right? And I knew that there was oxygen in the water. Somebody once told me that. Okay. So when they talked about oxygen being in the water, I'm going to draw a water molecule here. And again, my pen is still sometimes a little funky, so hopefully it'll work. So here's the water molecule. And again, this is the partial. There went the craziness. Well, let's get rid of this part here. So there was my water molecule. Let's see if I can get it let's see if we can re-put it in here. And I'm just going to stop this and I'm going to try. Yep, good. So there's my water molecule. And we know that this side here is the partial negative and this is the partial positive, right? Well, when we talked about oxygen being in water, I literally thought this was the oxygen that the fish were using to breathe, right? Well, and then it never dawned on me till I was like in college. Now, wait a minute, if this was true, the fish use the oxygen to breathe, that means we would have a whole pond full of hydrogen, right? So there would be no more water left. So dissolved oxygen is actually what the fish are using, and that's a little bit different. So if we're talking about a water molecule here, and I'm going to clone this, so I'm going to give ourselves here a couple of water molecules. And what happens with the water molecule is that it has the ability to kind of dissolve, if you will, encapsulate, if you will, the oxygen molecule, okay? So I'm going to attempt here at drawing oxygen again, and I'm going to just do that, hopefully here. Let's see if I can get rid of this. Let's see if I can do that. Oh, slow. Well, I'm going to pause here. Okay, so now I've got kind of a model of what dissolved oxygen looks like. So there is a connection here of the partial positive of the water being connected to these lone pair of electrons of the oxygen molecule, right? So there's an attraction here. And remember, the idea is that as we increase the temperature, that means the solubility of this oxygen will decrease. Well, how could that happen? Well, as we're increasing the temperature, what we're allowing for is for this water molecule to actually expand. So these are going to spread out even further, right? Breaking this attraction between the partial positive of the water molecule and these lone pairs of electrons, and it's going to allow for the oxygen to escape, okay? So this is why fish kills. Have you heard of fish kills? Like fish will die in pond waters, river waters, if it's real shallow and the water is warm, okay? Because there isn't enough dissolved oxygen in the water. Very common in shallow lakes and streams are to have fish kills in the summer months. And of course, they're more prevalent down south than they are here because the temperature can get much hotter. So the main thing to remember is the solubility of gases is the opposite of the solubility for solids in water. Okay. All right. Well, this is kind of what your homework will be like. And this looks like kind of like the lab you had done as well. And it says that you will have to interpret some of this data. So it says, according to the graph in Model 2, so this is Model 2, what is the solubility of substance A at 30 degrees? So you would just look at 30 degrees here, and you're going to go to substance A, and you would say, okay, that looks like it's probably somewhere around 48. I'd say about 48 grams. So you would type in 48 grams of substance A can dissolve into, and again, you're looking at this over here. It looks like it can dissolve into 100 grams of water, which, remember, since the density of, there we go. Since the density of water is 1, it can also be 100 milliliters of water. It says, describe the trend in solubility for substance A and B as temperature increases. So hopefully you would agree with me. As temperature increases, the solubility increases, right? Number 14, probably more like what you'll see also on the homework for tonight, is if a saturated solution of substance A in 100 grams of water is cooled from 30 to 10, what mass of solid solute would crystallize out? And you'd have to show your work. So you're starting with substance A at 30 degrees, and so we're going to say that that is at 48 grams. And then when you get down to 10 degrees, it looks like you're somewhere, maybe around, I don't know what that looks like. So 48, I'd say, to 28, right? So you're going to show your work, and you're going to say, okay, it was originally at 48 grams, and I got that from this point right up here. So right here, I'm evaluating that as 48 grams, and I'm subtracting, once it cools, what this point is. So I'm going to call that 28 grams. And so roughly about 20 grams, oops, I don't know what's happening there, 20 grams of solute would crystallize out, okay? Finally, if a saturated solution in substance B is 50 grams of water, and it's warmed to 50, what mass of solute would need to be added to make the solution saturated again? And you would do the same process. However, now you're looking at B, and you're starting from 30, and you're going to 50, so you're looking at that difference. And I see that difference as being about 9.5 grams. So that's what your homework's going to be like tonight, as far as interpreting the solubility curves. Okay, so Henry's law then is related to gases and solubilities. With Henry's law, the solubility of a gas in a liquid is directly proportional to the partial pressure of that gas on the surface of the liquid. And this is really common in our carbonated beverages. Beverages get their CO2 by the bottling plant injecting carbon dioxide into the liquid in order for it to be dissolved. So here's the CO2 that would be in this headspace right here above the liquid. And Henry's law says the amount of CO2 that's in the liquid is directly proportional to the amount of CO2 that's in that headspace. So now what happens when you open this bottle up? You guys know that fizzing occurs. That's because all of this CO2 that's here is released because this is higher pressure than out here. And all of the bubbles will then want to escape to the surface because of that equilibrium in pressure. The pressure on the outside is going to be equal to the pressure on the inside, and so those gas bubbles are going to want to escape. It's also the reason why, if we think about warm pop, okay, if you want to keep the carbonation of your pop, you've been told put it in the refrigerator. That's because at lower temperatures, it's going to be able to retain and hold that water or that gas at a better temperature, okay? And finally, I just want to talk about factors that affect the rate of dissolving and also affect the rate of solubility. So there's a couple here that we're going to talk about. The first is a surface area. So if you have a crushed powder versus more of a a larger powder or larger rock or crystalline forms, this is going to dissolve faster because there's more surface area. We also know that stirring gives you more chances of collision for the solute and the solvent to come into contact with each other. So that's going to increase the rate of dissolving. And finally, temperature. And this is kind of getting back to that thought of the kinetic molecular theory that I was talking about, that as your temperature increases, that means the molecular motion is increasing. Your kinetic energy is increasing. So that means there's more movement of the solvent and more chances for that solvent to collide with the solute, and therefore increasing the dissolving. Okay, so that's it for today's lesson. Keep on working. Have a great day.